Large language models are undisputed engineering miracles of our modern era. They can write complex operating systems from scratch. They can debug thousands of lines of C++ memory leaks in a matter of seconds. They can pass medical board exams and analyze legal contracts better than most junior lawyers. But if you ask them a mathematical question that a 10-year-old child could answer in a heartbeat, like which is bigger, 9.11 or 9.9, they completely fail. They will confidently and aggressively tell you that 9.11 is the larger number. How is it physically possible that a trillion-parameter supercomputer running on thousands of advanced GPUs is mathematically illiterate? The answer has absolutely nothing to do with logical reasoning, and everything to do with how an AI fundamentally sees the world. Today, we are looking at the fatal flaw of tokenization. To understand this catastrophic failure, we must first break a fundamental illusion. An AI does not see numbers. It does not understand the base 10 numerical system. It does not even know what a decimal point actually means in geometry or mathematics. When you type a prompt into ChatGPT, the neural network does not receive your text directly. Neural networks are essentially massive calculators. They can only process matrices of numbers, weights, and biases. So, before your text ever reaches the brain of the AI, it passes through a translator called a tokenizer. Modern GPT models use a specific algorithm called tick token, which relies on a method called Byte pair encoding. Its only job is to chop your words and sentences into small fragments called tokens and assign a unique ID integer to each fragment. It is a text compression algorithm designed strictly for human language, not for mathematics. Let us look closely at how tick token breaks down numbers, because this is where the system collapses. If you input the number 123, the tokenizer might recognize it and keep it as one single token. But if you add just one more digit to make it 1,234, the tokenizer might panic and chop it into two random fragments, the token 12 and the token 34. But here's the crazy part. If you type the number 2024, it might keep it as a single token again, simply because that specific 4-digit number appeared millions of times in its training data as a calendar year. There is absolutely no consistency. In human mathematics, the position of a digit dictates its exact value. The 1 in 100 means 100. But for an AI, because the tokenizer arbitrarily slices numbers apart based on internet frequency, the mathematical positional value is completely destroyed before the neural network even starts calculating. Now we have the tools to solve the 9.11 versus 9.9 paradox. When you feed these exact numbers into the tokenizer, it does not see them as cohesive decimal values. It shreds them into pieces. 9.11 becomes 3 separate tokens, the integer 9, a punctuation period, and the integer 11. 9.9 also becomes 3 tokens, the integer 9, a punctuation period, and the integer 9. The decimal point is treated just like a comma in a sentence, not a mathematical operator. When the neural network compares these sequences, it reaches the final tokens. It compares the isolated concept of 11 with the isolated concept of 9. Since the token for 11 represents a larger whole number than the token for 9, the AI predicts that 9.11 must be larger. It is not failing at math, it is failing at data parsing. This entire paradox is the hidden cost of data compression. Tokenization was engineered to make processing massive blocks of text fast and computationally cheap. It groups common letters and numbers together so the attention mechanism has to read fewer units, saving GPU memory. By optimizing exclusively for linguistic speed, we accidentally sacrificed mathematical precision. Until we build future architectures that can natively parse structural mathematics without forcing it through a text compression filter, large language models will remain fundamentally dyscalculic by design. They are brilliant readers, but terrible accountants. Subscribe to Latent Engineering to see the real mechanisms inside the black box, and I will see you in the next one.